Interestingly though, Gene Parker proposes 5 meters of shielding for cosmic rays with energies of only 2 GeV. If the material is water, it has to be 5 meters deep, so a spherical tank containing a small capsule would have a mass of about 500 tons. Larger, more comfortable living quarters would require even more. By comparison, the space shuttle can only carry a maximum payload of about 30 tons. Water is commonly proposed because astronauts would need it anyway, and because it is rich in hydrogen. Heavier elements make less effective shields because the extra protons and neutrons in their nuclei fall in one another's shadows, limiting their ability to interact with the incoming cosmic ray. To increase the hydrogen content, engineers could use ethylene, which has the further advantage that it can be polymerized to polyethylene, a solid, thereby avoiding the necessity for a tank to contain it. Even so, the required mass would be at least 400 tons, still not feasible. Pure hydrogen would be lighter, but would require a heavy pressurized vessel. Eleanor Blakely, a radiation biologist for the Life Sciences Division at Lawrence National Laboratory, also spoke of ethylene shielding as well as the possibility of shielding spacecrafts with its actual fuel tanks.
Yes, I was just wondering if you could speak to how difficult it would be to shield a spacecraft or even a spacesuit against different types of radiation.
Yes, you ask another good question. The only problem is that particles undergo a process called fragmentation. So if a particle comes in and hits like an aluminum shielding, it actually fragments into an array of particles of lower atomic number. So you actually have a higher fluence on the inside than you would have on the outside. So there's been recent study by NASA of the materials of the spacecraft, because hydrogenous materials like shielding, polyethylene shielding, can reduce just by the different Z of the impact of the ions coming in from space. So shielding has limitations from that point of view. However, I talked to an astronaut that his vision is that, of course, what you want to do is minimize the exposure to Mars. So he's a big proponent of other alternative propulsion, and he would like to put the propulsion material, which is hydrogenous, in big tanks around the spacecraft. Now that would really ruin your view, but it certainly would shield you, and so they have lots of things under study just to examine different alternative shielding.
Obviously, Apollo could never have been shielded with its own propellants, as the majority of which was spent right at the beginning of the trip. It should also be noted that Apollo used aluminium shielding, which, by Dr. Blakely's admission, would increase the risk of particle fragmentation, and thus worsen the radiation problem.
So if a particle comes in and hits like an aluminum shielding, it actually fragments into an array of particles of lower atomic number. So you actually have a higher fluence on the inside than you would have on the outside.
In his Scientific American article, Gene Parker lies down 3 different plans. Plan 1. Material shield. A large mass around the astronauts absorbs the incoming radiation and the secondary particles it produces. A spherical shield of water, 5 meters thick, provides the same protection that Earth's atmosphere offers at an altitude of 5,500 meters. It's simple and guaranteed to work, but way too heavy. Plan 2. Magnetic shield. An electromagnet pushes incoming particles back into space to deflect the bulk of cosmic rays, which have energies up to 2 GeV, requires a magnetic field 600,000 times as strong as the Earth's equatorial field. To suppress the field inside the living quarters, the spacecraft designers could add a second inner electromagnet ring. But the cancellation is only partial and greatly increases the complexity of the system. It's much lighter than the material shield, but offers no protection along axis, and the strong magnetic field may itself be dangerous. Plan 3. Electrostatic shield. Firing a beam of electrons into space causes a positive charge to build up on the spacecraft. This charge repels cosmic rays. To deflect particles with energies up to 2 GeV, the ship would have to be charged to 2 billion volts. It has no gaps in coverage and no hazardous magnetic field, but it creates a nasty influx of negatively charged particles, and requires a gargantuan electric current. On page 200, Malden also discusses the idea of using electric or magnetic shielding to repel away particles as high as 10 GeV. If protons and other nuclei up to 10 GeV in cosmic rays, which inevitably are ions, are the primary radiation problem, then potential of negative 10 billion volts would be needed to repel those protons. Again, the cislunar cosmic radiation has energies as high as 10 GeV. Evidence for this can be found within Malden's book itself. On page 197, he writes, "Observations near Earth are a poor guide because Earth's weak magnetic field protects us from cosmic particles below about 100 GeV, and reduces the intensity by 10 or more up to 10 GeV. Now how could John Malden have this data if the cislunar radiation were considerably less harsh than the interstellar radiation, as Windley alleges? The fact is, Malden clearly proposes this shielding for GeV protons, and even states that such particles exist in the geospaced region. These statements from both John Malden and Gene Parker indicate that the radiation encountered on the Moon either requires electric, magnetic, or thick solid shielding to be overcome. This adds strong evidence that the 2-meter shield proposal is not only for long interstellar journeys, as Windley alleges. In spite of these clear specifications, for years, Windley had frequently alleged that Ralph Rene misinterpreted Malden's proposal. That 2 meters of shielding is only necessary if one was to spend generations in interstellar space, the space occupied by stars. Windley, of course, makes no mention of these passages in which Malden specifies that he is talking about the radiation in the geospace region. As Rene points out, another problem with Windley's misrepresentation of the data is the fact that the further radiation travels into space, the more it dissipates.
Well, the further you get away from our sun, which gives us most of this crap, the less the radiation would be. It expands at the square of the distance, right? So, well, it's out by Pluto. The radiation needs 6 foot of water shielding, and down here closer to the sun, we need 14 feet or 50.
To sum up, 3 astrophysicists proposed shielding astronauts behind meters of material. Interestingly, OPEC's idea of tunneling under the lunar surface to hide from the radiation is exactly the precaution that Dr. Wernher von Braun took when he proposed a 50-crew expedition to the Moon back in 1953. As he states on page 70 of his book, Conquest of the Moon,
For maximum protection against cosmic radiation, we shall stay under cover as much as possible. Our headquarters must be located in a deep crack in the surface, giving us protection from both rays and meteorites. The crevice chosen for the lunar headquarters will be deep. We will require a depth of 65 to 100 feet for safety, with almost vertical sides.
Von Braun finishes up his talk on cosmic rays, saying,
Brief exposure to cosmic radiation probably won't hurt us.
Of course, in 1953, the real dangers of cosmic radiation were not entirely understood. Today, we know that the cosmic radiation in cislunar space is as high as 10 GeV.